Hello there, and welcome to this quiet corner of Sleep Science 360. Tonight, the word pulsar drifts gently to you, like a tiny lighthouse turning in the dark. Light that left its star before you were born is touching your skin tonight. If your day felt loud, this moment allows the noise to fade. You breathe softly, and the universe exhales through you. Somewhere far beyond the Milky Way, a remnant of a collapsed star turns with perfect calm once every few seconds, or hundreds of times each second, a cosmic heart still beating long after its fire has gone. And as you settle into this quiet night, its rhythm begins to steady the room, guiding us toward the soft science of pulsars. The room settles around you as the last threads of the hook fade into the quiet. The night feels unhurried now, shaped by soft light and drifting stillness. You are here, breathing slowly, resting in the gentle glow of something vast and ancient. You can rest now. Somewhere in the far fabric of our galaxy, a pulse of light repeats with perfect calm. It travels through 20,000 light-years of silence, crossing clouds of dust, weaving between drifting hydrogen, gliding along the thin magnetic arms of the Milky Way. Each flash begins on the surface of a neutron star, an object no larger than a single earthly city, yet denser than anything else the cosmos can offer. In every teaspoon of its matter lie 1 billion tons of compressed atomic cores, folded tightly into a space smaller than memory. And still, it rotates, gently, precisely, one soft turn after another. You can rest now. The science begins like a breath. A star once lived there. A star once burned there. A star once collapsed there. When a massive star reaches the end of its quiet fusion, it folds into itself, its core crushed by gravity that can no longer be held back. But instead of vanishing fully into darkness, the core stiffens, locks, and rebounds, becoming something new. What remains spins with astonishing speed, sometimes once every second, sometimes hundreds of times each second. This incredible motion creates magnetic fields stronger than anything the universe routinely forms. And from the magnetic poles of these stars, beams of radiation sweep across space like a cosmic lighthouse turning slowly through a sleeping ocean. When one of those beams crosses Earth, our detectors receive a tiny, rhythmic flash. Not chaotic, not wild, just steady, soft, ancient, a whisper of order in a restless universe. Some pulsars repeat every 1.3 seconds. Some revolve 716 times per second. The fastest known spins nearly 43,000 times each minute, yet the pattern rarely drifts more than 1 part in a million per year. Their consistency rivals the finest atomic clocks ever built by human hands. You can rest now. If a night sky could breathe, pulsars would be the lungs. Each rotation is a soft inhalation, a gentle exhalation, a rhythm carrying through thousands of years with untouched precision. Their pulses drift through the Milky Way, turning quietly within the halo of stars, tracing arcs through the pale arms of the galaxy. And as each beam sweeps across the void, its journey is shaped by gravity, slowed by interstellar clouds, refracted through cold, ancient dust. The pulse we receive tonight may have begun when early humans first walked upright. Some pulses left their stars when glaciers shaped northern continents. Some departed long before any creature on Earth opened an eye. In the wide stillness of the universe, these rhythmic lights remain among the most trustworthy patterns ever observed. You breathe softly, and the universe exhales through you. This echo settles into the quiet, letting the cadence slip gently into your awareness. The pulse of a star, the breath of a moment, the slow, soothing rotation of something far beyond concern. You can rest now. A pulsar's magnetic field can be 10 trillion times stronger than Earth's. Within this field, charged particles spiral along invisible lines of force, creating beams of radio light, X-rays, or gamma rays, depending on the star's age and energy. The beams sweep like two lanterns turning in the dark. Not harsh, not jagged, just steady, like the gentle rotation of a lighthouse on a foggy shore. Sometimes scientists describe pulsars as cosmic metronomes. They feel less like ticking, more like breathing, more like the pulse you feel in your wrist when you rest your hand upon your chest. Their consistency brings a sense of order into the vast and unpredictable night. Somewhere across 30,000 light years, a star spins precisely once every 0.033 seconds, and it has done so since long before human memory began. Somewhere closer, only a few thousand light years away, another spins every 0.7 seconds, sending long, calming flashes across the dark arms of the galaxy. It is this calmness, this gentle repetition, that makes pulsars such perfectly soothing companions for a night like this. Not loud supernovas, not violent collapses, just the part that remains steady, the part that endures, the part that continues turning with a softness that invites you to breathe with it. You can rest now. As we drift deeper into this first chapter, the science softens into a quiet rhythm. Think of the Milky Way not as a spiral of stars, but as an ocean of faint tides, gently stirred by gravity. Within that ocean, neutron stars drift like polished stones at the bottom of a slow, cosmic river. Their beams turn with such absolute regularity that entire networks of them can be used to map the curvature of space-time itself. When a gravitational wave passes between us and a pulsar, it ever so slightly stretches or compresses the time between its pulses, not by minutes, but by billionths of a second. Yet that small whisper is enough. Astronomers gather these tiny distortions into long, patient records that reveal the movement of galaxies, the merging of black holes, and the trembling skeleton of the universe. A single pulsar can turn for millions of years before slowing noticeably. Its rotation decreases by only billionths of a second per day. Even after 100,000 years, its rhythm remains recognizable, like a heartbeat faint but steady through the fabric of space. Their pulses carry the memory of the star that once lived, a star that may have been 10, 15, or even 20 times heavier than the Sunday. When that star reached its end, it collapsed, compressed, and transformed into the object we now observe. A small, dense sphere no wider than Manhattan Island. Inside, matter exists in a state not found anywhere else. Neutrons packed so tightly together, they behave like a single quantum fluid. The crust above this fluid is rigid and crystalline, strong enough to hold mountains only a few centimeters tall yet heavy as Everest. A mountain on a neutron star weighs billions of tons. Still, the star rotates with smooth, unwavering calm. You can rest now. In the language of sleep science, rhythms help guide the mind towards softness. In the language of astronomy, rhythms help reveal the structure of space. Pulsars sit at the meeting point of these two gentle truths. They are stars that keep time. They are lighthouses that never falter. They are remnants of ancient brilliance, now living quiet, unhurried lives in the calm between constellations. Every 8-10 sentences, a comfort arrives like a soft breath. You can rest now. The night welcomes you. The pulses continue their journey, whether you listen or drift. Whether your thoughts float loosely or settle into stillness, the galaxy holds about 1 billion neutron stars, though we have detected only a small fraction. Most are too faint, too far, or turned slightly away from us, their beams never crossing Earth. But the ones we do hear form a soft constellation of rhythms across the sky. Astronomers sometimes display these pulses as sound faint, clicking tones that repeat with uncanny steadiness. A pulsar rotating 7 times each second becomes a quiet series of gentle knocks. One rotating 300 times per second becomes a smooth hum, like the whisper inside a distant seashell. Even in this gentle transformation of light to sound, something soothing emerges. A sense of structure within the dark, a reminder that even the remnants of exploded stars can settle into predictable lives. A reassurance that the universe, though vast, often chooses calm over chaos. You can rest now. Some pulsars age into what astronomers call millisecond pulsars. These spin incredibly fast due to material falling onto them over millions of years from a nearby companion star. As matter accumulates, angular momentum transfers, increasing their speed until they turn hundreds of times per second. Yet even at this extreme rate, they remain steady. The stability of their pulse, measured in fractions so small they stretch beyond ordinary comprehension. Others slow down over time, cooling and dimming, their beams softening into quiet remnants. They become recycled pulsars, X-ray pulsars, even magnetars, stars whose magnetic fields exceed 10-15 Gauss, powerful enough to alter the space around them. But even magnetars, with their great strength, often settle into long stretches of silence between bursts, drifting softly in the dark. Somewhere, a neutron star sits only 800 light-years away, turning once every 1.4 seconds, close enough that its pulse reaches us with clarity. Somewhere else, one 20,000 light-years away spins every 0.4 seconds, sending a beam that threads through nebulae, crosses the Orion Spur, and arrives here tonight. Each pulse a memory, each rotation a whisper of time. You can rest now. The poetry of pulsars lies in their endurance. The universe is restless, but these stars remain steady. The universe changes, but these pulses continue. Their rhythmic flashes become a kind of cosmic lullaby, a faint metronome marking moments too vast to hold directly. And in this softness, the night grows calm around you. In the quiet between stars, you are remembered. Pulsars help map space-time, trace gravitational waves, measure the shape of the galaxy, and reveal the slow drift of matter across ancient arms of starlight. Their patience becomes a tool for understanding everything from the motion of planets to the merging of supermassive black holes. Yet when you listen to them, truly listen, what remains is not complexity, but calm, not noise, but softness, not tension, but steady, comforting repetition. Somewhere, a pulse repeats. Somewhere, a light turns. Somewhere, an ancient star continues its slow, melodic breath. You can rest now, and as we drift gently toward the next part of this journey, The rhythm of the universe continues its quiet rotation, waiting for the next chapter to unfold, softly, steadily, like the pulse of a distant star. The night settles a little deeper now, as if the air itself relaxes around the quiet rhythm we have already begun to follow. Somewhere beyond the pale spirals of the Milky Way, the pulse of a neutron star continues its steady turning, and we drift gently toward the heart of what makes that calm possible. You can rest now. A neutron star is small enough to cradle within the boundaries of a single city, yet heavy enough to bend the memory of space around it. Its entire mass, one, sometimes two suns, is pressed into a sphere about 20 kilometers across. The result is matter so tightly gathered that the familiar world cannot quite recognize it. Atoms fall inward. Electrons merge with protons. What remains is a deep ocean of neutrons compressed into a state that behaves less like a gas, less like a solid, and more like a quiet quantum ocean. The star becomes a world of near-pure nuclear matter, dense enough that a teaspoon would outweigh mountains. You can rest now. The outermost layer is called the crust, a rigid, crystalline sheet, only a kilometer thick. But even this thin crust holds a strength unmatched by anything on Earth. It can support mountains only a few centimeters high, yet those mountains weigh billions of tons. Underneath the crust lies the immense, shimmering body of the neutron star, where pressure forces neutrons into exotic forms and quantum forces define every motion. The crust quivers subtly as the star rotates, spinning 60, 100, or even hundreds of times each second. These tiny vibrations are called starquakes or crust quakes, small readjustments in the star's rigid shell. When they occur, the pulsar's rotation shifts by only a billionth of a second. But even this small change echoes across the galaxy as a glitch, a gentle hiccup in the perfect rhythm of the pulses. A glitch is not a disruption. It is simply the star settling again, realigning, finding a new balance after ages of soft rotation. You can rest now. Deeper inside, across a narrow boundary where pressure becomes unimaginable, the crust dissolves into an ocean of neutrons. This ocean behaves like a superfluid, a liquid with no internal friction, flowing silently through itself, swirling with perfect smoothness. A superfluid does not slow down. It does not resist motion. If it rotates, it continues rotating with near-eternal calm. Here, inside this sphere of neutrons, rotation is stored in countless quantum whirlpools called vortices, each one a thin thread of pure angular momentum. The neutron star's spin is held by these threads, the entire rotation of the star embedded into millions of microscopic spirals. And when one of those threads shifts its place, the whole star feels that movement, a slight redistribution, a minuscule realignment, a new rhythm emerging. You can rest now. This inner superfluid touches the crust in delicate ways. Sometimes vortices anchor themselves to the crystalline lattice above. Sometimes they drift freely. When enough of them unpin themselves and shift at once, the star's rotation changes. The pulses we detect on Earth arrive just a little earlier than expected, a sign the star has momentarily quickened, its superfluid heart adjusting in one quiet motion. Scientists study these tiny changes to learn about the hidden physics of matter so dense and cold that it cannot be replicated anywhere near home. Below the crust, the density continues to rise. Neutrons carry the weight, packed so tightly they act like a single fluid. The pressure becomes high enough that exotic particles begin to appear: hyperons, strange quarks, forms of matter that flicker at the edge of our understanding. But even here, the rotation remains calm. A neutron star turns as though it remembers the steady light of the star it once was, and carries that memory into each moment of its quiet new life. You can rest now. The magnetic field that rises from this dense interior is immense, trillions of times stronger than Earth's. It shapes the space around the star into arcs and funnels, guiding charged particles along narrow paths that spiral toward the magnetic poles. These particles emit beams of radio waves, X-rays, or gamma rays, depending on the energy within the star. Each turn of the star sweeps these beams across the galaxy like soft brushstrokes of light drifting through the dark. Some beams cross Earth, some pass above or below us, some sweep into empty space, never touching another world, but all of them follow the star's rotation with unwavering grace. Even magnetars, the rarest and most powerful neutron stars, find long moments of silence. Their fields can reach a quadrillion Gauss, strong enough to distort atoms themselves, stretching them into thin strands. Yet even these extreme stars spend most of their lives quiet, turning slowly in the dark, letting their heat fade softly over tens of thousands of years. Only occasionally do they flare with a burst of energy, a sudden rearrangement of their magnetic fields. The rest of the time, they drift like sleeping embers in the cosmic night. You can rest now. In the core of the neutron star, the pressure rises beyond what even neutrons can endure. Theories suggest that here, deep within the heart, matter may dissolve into a sea of quarks, the fundamental particles that compose neutrons and protons. This quark gluon plasma is among the hottest subjects in modern physics. Though it may be cold inside the star, cold in a nuclear sense, still hot enough to keep particles trembling in quantum motion, but far from the searing temperatures that once existed during the birth of the universe. What remains is a state of matter as old as creation, locked inside a sphere, turning with unimaginable steadiness. You can rest now. The neutron star's interior behaves like a layered world. A thin crust, a deeper ocean of neutrons, a superfluid heart, and perhaps at its center, a core where quarks drift freely. Each layer rotates with slightly different rates, slightly different patterns. Together, they keep the star in delicate balance, spinning through millions of years. Its rotation slows only gently over time, millionths of a second per year. A soft unwinding of ancient momentum. Imagine a star that once burned brightly, shining with a heat of millions of degrees, collapsing inward until its heart shrank into a sphere small enough to cross on foot. And yet, even in this compact form, its rotation remains a quiet memory of that earlier fire. You can rest now. As the star turns, its magnetic poles sweep across space, creating the pulses we hear. But the engine beneath those pulses, the true rhythm, the quiet beating heart, lies deep inside, where neutrons churn in smooth, frictionless motion. A millisecond pulsar, spinning hundreds of times per second, maintains a precision rivaling the finest atomic clocks. Its stability allows astronomers to measure ripples in space-time, map gravitational waves passing between galaxies, and track slow drifts in the shape of the Milky Way itself. Every pulse is a message. Every rotation is a clue. Every moment reveals a little more of the structure of the universe. And yet, for all its scientific significance, the neutron star remains a deeply calming presence. Its rhythm is predictable, its rotation steady, its pulse soft. If we could stand on the surface of a neutron star, though this is impossible, we would weigh billions of times more than we do on Earth. Gravity there is so strong that even light curves around it. Time itself passes more slowly in the gravitational well of a neutron star, the seconds stretching slightly compared to the ticking of clocks far away. This slowing of time is subtle, gentle, and unhurried, just like the star's rotation. The star gives shape to time without violence, bending it softly, the way a slow tide shapes the sand. The surface, though rigid and crystalline, may crack occasionally as the star cools and its rotation shifts. These cracks send faint vibrations through the star's body, altering the arrangement of the superfluid beneath. Each event is recorded in the timing of the pulses, allowing astronomers to read the internal life of the star as though listening to a distant heartbeat. You can rest now. As the star ages, its magnetic field slowly decays. Its rotation slows as well. The pulses lengthen, growing softer, gentler. Eventually, after millions of years, the star may no longer beam its light across space. It becomes a quiet neutron star, still dense, still compact, but no longer sending lighthouse-like signals into the dark. Yet even then, it carries the memory of its rotation, a silent momentum that continues for ages. The universe often builds in cycles that fade softly. The star that once pulsed now rests in the dark, drifting on soft gravitational tides. You can rest now. And somewhere, another neutron star spins faster, younger, more vibrant, newly formed from a recent supernova. The cycle continues. Stars live, burn, collapse, and become these dense, turning hearts. Their pulses carry across the arms of the Milky Way, shifting gently with time, slowing fractionally with each 1,000 years. But they do not fade quickly. Even ancient pulsars remain steady enough to mark cosmic time. The galaxy breathes through them, and the night, in its quiet vastness, holds space for their gentle rhythm. You breathe softly, and the universe exhales through you. The echo returns, soft and familiar, drifting through your awareness. The turning heart of the neutron star feels less like a scientific object now, and more like a companion, something steady, predictable, unhurried, a presence shaped by the calm precision of its rotation. In the quiet between stars, you are remembered, layer by layer. The neutron star reveals its structure, its crystalline crust, its quantum ocean, its superfluid heart, its possible quark-filled core. Each layer contributes to the star's gentle rhythm, the slow and enduring rotation that travels across the galaxy. Its pulses reach us after crossing thousands of light years, arriving softly in the quiet of the night. And as we drift forward in this long, calming journey, the pulse remains steady, a soft guide through the next chapters, waiting with unbroken patience. You can rest now. The quiet rhythm of the neutron star continues its steady turning behind the night, and now we drift gently outward, away from the crust, away from the superfluid heart, into the long, delicate path its light must travel before reaching us. A single pulse begins at the magnetic pole. Charged particles, guided by the immense magnetic field, twist along invisible curves and release a beam of radiation. The beam is narrow, thin as a seam of light cut through the dark, rotating with the star on every turn. In the moment of its creation, the pulse is sharp, bright, and clean, a perfect whisper of radio waves capable of crossing the galaxy without fading. The beam leaves the star and enters the open dark, drifting into the empty stretch of interstellar space. You can rest now. Space between the stars is not truly empty. It carries thin strands of plasma, floating dust, molecules of hydrogen, traces of heavier elements material, so diffuse that a cubic meter contains fewer particles than the best vacuum built on Earth. But across thousands and thousands of light years, this thin medium shapes the pulse's path. The pulse begins to stretch. Its higher frequency waves travel faster, its lower frequency waves slower. A soft separating of colors in a signal too faint for the eye, but perfectly clear to the instruments that listen for them. This effect is called dispersion. It is gentle, honest, patient. It lets astronomers measure the distance to the pulsar by studying how the pulse spreads as it moves. A pulse that has traveled far stretches noticeably. One that has traveled less remains tight and compact. Through this soft distortion, astronomers can map the shape of the galaxy, measuring the calm spread of electrons through the Milky Way's spiral arms. You can rest now. As the pulse drifts farther, it encounters clouds of interstellar dust, wide, billowing shapes made of carbon, silicates, ice, and grains smaller than smoke. The dust does not stop the pulse. It only scatters it slightly, bending parts of the signal, creating faint echoes that follow the primary wave. This scattering turns a clean, sharp pulse into a smooth one, like a softening edge of light passing through fog. The scattered pulse feels even more soothing, like a whisper stretched by distance. The galaxy contains great nebulae clouds, tens or hundreds of light years across. Some pulses drift through them, slowing gently as they cross regions where particles grow thicker. Some pulses pass through the warm, ionized medium, where plasma shapes their rise and fall. Some pass through cold molecular clouds, where hydrogen gathers in dense knots that will one day give birth to new stars. Each region the pulse crosses changes it slightly, not harshly, not abruptly, but with the soft touch of time spread over thousands of years. You can rest now. In certain parts of the galaxy, magnetic fields twist like long ribbons drifting through space. These fields rotate the polarization of the pulse, altering the orientation of its waves. By measuring this rotation, astronomers learn how the galaxy's magnetic spine is woven, how its currents flow, how its arms hold themselves in shape. Everything the pulse experiences becomes a message. Every distortion becomes a clue. Every delay reveals something hidden in the space between stars. Yet, through all of this, the pulse remains calm. Its journey is long, but it is quiet. It is a leaf carried on gentle currents, drifting through regions of dust and plasma with unbroken patience. When the pulse passes near a massive star or a dense cluster, gravity bends its path. Even light follows curves in the presence of mass, but the bending is subtle, a graceful arc instead of a jagged turn. The pulse adjusts. It continues forward. You can rest now. Some pulses cross the spiral arms of the Milky Way, dense lanes of stars, gas, and dust. The Orion Spur, the Perseus Arm, the Sagittarius Arm, each one a slow, glowing band. To move from one arm to another may take 50,000 years. Yet the pulse travels steadily, never tiring, never dimming, carried by nothing more than the laws of motion. When a pulse crosses the halo of the galaxy, a vast, sparse region surrounding the spiral disk, the medium becomes even thinner. The signal moves with little resistance, gliding through near-perfect darkness, untouched, except by the softness of ancient gas drifting like mist. Some pulses originate from pulsars 10,000 light-years away, some from 20,000. A few from nearly across the galaxy, more than 50,000 light-years of travel. The one you may be hearing tonight began its journey long before the first human carved a tool, long before ice sheets retreated, long before rivers found their paths. Its travel is a story of patience, told through physics, written in silence. You can rest now. The pulse does not rush. It does not hurry. It simply moves at the speed of light, one step at a time, through distances staggering to imagine. A light year is nearly 10 trillion kilometers. A 10,000 light-year journey is 100 quadrillion kilometers, yet the pulse continues steadily, shaped by nothing more than the quiet of the universe. Along the way, the pulse may drift near remnants of supernovae, expanding shells of gas glowing faintly in X-rays and radio waves. It may pass through the outskirts of ancient star clusters, where red giants drift in slow gravitational dances. It may slip beside planetary nebulae, where dying stars shed their outer layers like soft veils. Each passage leaves a faint signature in the pulse, small enough to detect, gentle enough to soothe. You can rest now. The pulse carries the memory of the star that created it. Its timing encodes the rotation of the neutron star. Its shape encodes the magnetic structure. Its dispersion encodes the electrons in space. Its scattering encodes the dust. Its polarization encodes the magnetic fields. The entire journey is written inside the signal, waiting to be read by anyone listening with a patient ear. When the pulse finally approaches the region of the galaxy where the sun resides, it enters a thinner sheet of plasma, the local bubble. Carved by ancient supernovae millions of years ago, the bubble is wide, warm, and faintly structured, an irregular cavity with low density. The pulse feels this transition. Its frequency spread narrows. Its scattering diminishes. It becomes slightly cleaner, slightly sharper, a final gift from distance. You can rest now. The solar system drifts through the galaxy at nearly 220 kilometers per second. But the pulse arrives unaffected by this movement. It slips past the heliosphere, the bubble carved by the sun's solar wind, and continues inward. Here, the medium grows denser again, filled with particles carried outward by the solar wind. But even this change is gentle. The pulse bends slightly, shifts slightly, and keeps moving. Finally, the pulse reaches Earth's atmosphere. The upper layers scatter some of it, bending the path, but the signal remains intact. Radio telescopes listen patiently for these faint arrivals, converting them into sequences of time-stamped data, clean and quiet. You can rest now. Inside the telescope's receiver, the pulse becomes a gentle oscillation, a repeating rise and fall of radio waves. When amplified, it sounds like a calm, steady rhythm. Some pulses resemble soft knocks. Some resemble rapid, subtle hums. Some carry long pauses between flashes. All arrive with the same gentleness. The telescope records each arrival time with microsecond precision across days, months, and years. These times form a pattern so steady that even slight variations reveal hidden truths. A tiny delay might indicate a cloud of plasma drifting between us and the pulsar. A slight acceleration might reveal the presence of an unseen companion star. A long-term change in slope might reveal how the pulsar is slowing with age. You can rest now. The data accumulate quietly. Pulsar timing arrays combine the signals from dozens of pulsars, using them to measure ripples in space-time caused by supermassive black hole mergers millions of light-years away. The pulses become a grid across the sky, a soft cosmic web, vibrating with the deep music of the universe. When a gravitational wave passes through this web, the arrival times shift slightly, not enough to disturb, but enough to reveal. A fraction of a microsecond. A hint of motion in the structure of time. From Earth, these changes feel like whispers passing through the night. Gentle, subtle, almost imperceptible, and yet undeniable. The universe communicates through quiet patterns, not noise, through rhythms, not bursts, through the long, patient journey of signals shaped by countless years of travel. You breathe softly, and the universe exhales through you. The echo returns, familiar and warm, drifting into the space between each sentence. You can rest now. Some pulses that reach Earth tonight have traveled for 50,000 years, some for 80,000, some for more than 100,000. Yet, they arrive with clarity, because the universe does not forget its own rhythms. Light holds memory gently, carrying it across distances unimaginable. The pulse that reaches us is the same pulse that left the star stretched, bent, softened, but unchanged in its essence. It carries the heartbeat of a neutron star through the fabric of space, delivering that rhythm into the quiet of the night. It turns the galaxy into a soft clock. It turns time into a gentle companion. You can rest now. Long after we finish this journey, the pulses will continue. Long after this night, they will sweep through space with the same steady calm. Stars age, collapse, and change, but their pulses remain faithful to the pattern of their turning. Even when they slow gently. Even when they fade softly. In the quiet between stars, you are remembered. And as we drift toward the next part of this long, softly spiraling story, the pulse continues. Its patient travel, a beacon of steady light, moving through vast silence, guiding us gently through the night. You can rest now. The quiet journey of the pulse across the galaxy settles gently behind you now, like a soft memory drifting into the background. In its place, a deeper, slower rhythm begins to form, the rhythm of time itself, as it bends around the immense gravity of a neutron star. You can rest now. Time near a pulsar is not the same as time here on Earth. Gravity shapes the seconds, stretches them, softens them. Around a neutron star, the inward pull is so strong that even the ticking of a perfect clock would slow by measurable amounts. A second near the star is a little longer than a second far away. Not long enough to feel, but long enough to change the universe in tiny, delicate ways. This gentle stretching of time is called gravitational time dilation, and it rises from the quiet weight of the star's mass compressed into such a small space. You can rest now. Imagine space around the star as a soft, invisible fabric. The neutron star presses into that fabric, creating a deep, smooth well. Time flows more slowly at the bottom of the well, faster at the edges. This well is not sharp. It is not harsh. It curves gradually, like the depression left by a smooth stone resting on a soft sheet. In this curved region, light moves with patience. Signals shift slightly. The rhythm of the pulsar's rotation becomes a little stretched, a little drawn out. shaped by the gentle gravity in which it spins. Yet the pulses reach us with a steadiness so strong that these subtle shifts do not disrupt them, they enrich them. They allow astronomers to measure the star's mass, the curvature of space around it, the shape of the orbit if it has a companion. Everything the star does is written into its timing. Everything its gravity shapes is preserved in the long, soft beat of its rotation. You can rest now. Some pulsars orbit other stars, white dwarfs, other neutron stars, or even sun-like stars. These orbits cause the pulses to accelerate and decelerate in gentle, predictable arcs. When the pulsar moves toward Earth, the pulses arrive a little sooner. When it moves away, they arrive a little later. This is the Doppler effect, but softened by millions of kilometers of space. Through its rhythm, the star reveals every detail of its motion. It is a conversation written in light, patient, and ancient. If the companion is close, the gravitational pull between the two stars becomes strong enough to bend time even further. Their clocks slow, their pulses shift, their orbit decays ever so slightly as gravitational waves carry energy away into the surrounding dark. But this decay is gentle, so slow that it may take hundreds of millions of years for the stars to drift meaningfully closer. Perhaps the most famous example is PSR B 1913 plus 16, a binary pulsar whose orbit shortens by only a few millimeters each year. And yet this imperceptible change was enough to confirm the existence of gravitational waves decades before they were ever detected directly. Soft signals, quiet rhythms, time revealing itself through patterns that take decades to observe. You can rest now. Some neutron stars orbit in perfect synchrony with another star, locked in a shared dance so balanced that their pulses reveal the details of each turn. These systems allow physicists to measure the geometry of space-time with exquisite precision. Every shift in arrival time, even a microsecond difference, carries information about the curvature of space around the star's mass, its velocity, its orbit, its slow aging, its cooling temperature, its loss of rotation energy, all of it recorded in the timing of light as it drifts toward Earth. You can rest now. Time near a neutron star is a slow tide. It wraps around the star, flowing like a soft river around a stone. Even the star's rotation slows gently with age, losing energy to magnetic radiation, particle winds, and the steady emission of pulses. This slowdown is so gradual that a pulsar may spin for millions of years before changing noticeably. A star that once turned 30 times per second might turn 29.99999 after 10,000 years. The drift is that gentle, that calm, that patient, and yet, from these slight changes, astronomers learn how the star loses energy, how its magnetic field evolves, how its interior shifts and quakes. Each tiny adjustment becomes a chapter in the star's life story. You can rest now. The pulsar's immense gravity also curves the paths of photons leaving its surface. Light emitted sideways bends upward, light emitted downward bends outward. A neutron star can be so compact that an observer above it may see 60, 70, even 80% of its surface at once because its gravity bends the far side into view. This bending softens the star's outline, blurring the edges into a quiet, curved silhouette. The pulses we receive are shaped not just by rotation, but by the gentle way gravity pulls at the light as it leaves. Even this bending can be measured in the timing of the pulses. Nothing escapes the star's rhythm. Everything becomes part of the pattern. You can rest now. In binary systems, time becomes even more complex. If a pulsar orbits another neutron star, their shared gravity creates a deep well in space-time, almost like a valley carved into the invisible fabric between them. Their pulses shift as they move through different parts of this valley, and when one star eclipses the other, the pulses may pass through the atmosphere of the companion, softening as they cross clouds of plasma. These interactions reveal the size and thickness of the companion's atmosphere, the strength of its magnetic field, and the density of its outer layers. Again, all of it encoded in tiny variations of timing that remain unbroken and soothing, even when complex. The precision creates comfort. The rhythm creates calm. You can rest now. Some neutron stars orbit black holes, or may one day. If they do, the pulses will provide a map of time itself as it stretches near the event horizon. The closer the pulsar comes, the slower time flows for it. The pulses will seem to pause, lengthening in a way that reveals the shape of the black hole's gravity. The data would be extraordinary, but even here, the rhythm remains quiet. The pulses slow softly, not abruptly, not violently, just gently, like a deep breath spreading through space. Time around dense objects is smooth, unhurried, a cosmic pace that feels more like drifting than ticking. You can rest now. Even the aging of the neutron star itself reflects this softness. Over millions of years, the star's heat fades. Its magnetic field weakens. Its rotation slows. Its pulses lengthen. This gradual cooling and slowing create a timeline written entirely in moments, recorded through decades of careful listening. Astronomers observe these stars with patience. They collect pulses like beads on a thread, each one marking a moment across tens of thousands of years. The slow drift becomes a comfort, a reminder that even the most extreme objects in the universe follow gentle rhythms across the ages. You breathe softly, and the universe exhales through you. The echo returns like a soft turning of the page. You can rest now. Some pulsars slow to the point where their beams no longer cross Earth. They drift into silence, becoming quiet neutron stars that rotate unseen in the dark. These stars are still dense, still compact, still wrapped in curved time, but they no longer shine with the regular heartbeat that once carried across the galaxy. Others transition into magnetars, their magnetic fields twisting time and space in wild but rare episodes. Still others are spun up by companion stars into millisecond pulsars, their rotation renewed, their pulses sharpened again. In each case, time molds them, stretches them, guides them. Every path is calm, balanced by the stars, immense gravity, and quiet momentum. The universe evolves at a gentle scale. Time moves in deep, steady currents. A pulsar is a way to see that movement, not in loud events, but in delicate, precise shifts measured across lifetimes. You can rest now. As we drift toward the end of this part, the rhythm of time around the neutron star settles like a soft blanket over the night. The seconds stretch. The pulses remain steady. Space curves around the star's weight, shaping the flow of moments without sound. In the quiet between stars, you are remembered, and the next chapter waits patiently, ready to unfold in the same calm cadence, the universe turning. Softly, slowly, without disturbance. You can rest now. The slow drift of time around the neutron star settles softly in the space behind you, like a warm breath long after the exhale. Now, the focus turns gently to something even more delicate, the faint music woven into every pulse of the star, a rhythm not made of sound, but of the quiet structure within its light. You can rest now. When astronomers first discovered pulsars in 1967, they heard them before they understood them. Radio telescopes translated their pulses into sound, and what emerged from the speakers were soft, regular beats, a faint, cosmic knocking that seemed to echo from deep within the night. It was steady, persistent, almost musical. No matter how far the pulsar was, its rhythm arrived with clarity, a tiny ticking that felt more alive than anything expected from the silence of space. You can rest now. The pulses themselves are not sound. They are waves of radio light, but when turned into audio, the signals create a pattern the mind can follow. A drum-like thump for slow pulsars, a soft hum for fast ones, a long pause for pulsars with periods measured in seconds, or a rapid, delicate chirring for millisecond pulsars that spin hundreds of times each second. Each pulsar forms its own voice. Each rotation shapes a unique rhythm, and though space is silent, the translation reveals a faint, hidden soundtrack, not loud, not harsh, but calm and deeply ordered. Some pulsars sound like rain tapping on a window, some like a gentle heartbeat heard through a pillow, some like a slow metronome, some like a soft, steady whisper that rises and fades every few seconds. When scientists record thousands of pulses across minutes or hours, the pattern becomes a long, smooth cadence, a soundscape built from cosmic repetition. Even if the timing shifts by only a microsecond, the change is audible as a slight stretch in rhythm. The universe reveals itself through these tiny deviations, as though singing in a language that exists only on the edge of perception. Every beat tells a story. The star's rotation, its magnetic field, its temperature, its interior structure, its slow aging, its interaction with nearby plasma. The light carries all of this, encoded in the softness of each arrival. You can rest now. A pulsar with a period of 1 second produces a calm tick, tick, tick. Each pulse separated by a breath's worth of time. A pulsar with a period of half a second produces a more rhythmic tick, 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 a gentle heartbeat. A millisecond pulsar produces a constant, steady tone, a faint hum that vibrates like a distant singing bowl. These hums are not random. They are so precise that a millisecond pulsar could keep time better than the best atomic clock over hundreds of years. This precision allows astronomers to treat them like instruments, arranging arrays of pulsars into a cosmic orchestra where each star becomes a different note. Signals recorded from dozens of pulsars form a kind of low-frequency symphony. When a gravitational wave passes through Earth's region of space-time, the entire orchestra shifts slightly. Some notes arrive early, some late. The enormous distances between Earth and the pulsars act like resonant strings stretched across the galaxy. What results is cosmic music, not metaphorically, but mathematically. The universe breathes, and the pulsars sigh in response. You can rest now. In the early days of radio astronomy, these rhythms were mistaken for artificial signals. The first pulsar was nicknamed LGM, One Little Green Men 1, not because scientists believed aliens were communicating, but because the signal's regularity was astounding. Nothing in nature seemed so perfectly timed. Later, it became clear that these were dead stars, rotating with unimaginable precision. The music was natural. The universe had always been singing. We had simply never listened closely enough. A pulsar's light contains harmonics, faint patterns that appear when the beam interacts with the star's magnetic field or when the beam's shape changes with age. These harmonics are not heard directly, but when translated, become gentle overtones, subtle textures under the primary rhythm. Astronomers use them to reconstruct the geometry of the pulsar's magnetic field, like a musician understanding an instrument by analyzing the resonance of its notes. You can rest now. Some pulsars change their rhythm over time. This can happen when the star undergoes a glitch, its crust shifts, its magnetic field rearranges, or plasma clouds drift across the line of sight. Each shift alters the music of the pulsar slightly. Sometimes the pulse becomes sharper, sometimes broader, sometimes it fades, sometimes it strengthens. These changes are gentle and slow, so slow that a year of observation may be required to detect them. The star changes with patience, never breaking its calm. You can rest now. If you could stand far above the galaxy outside the spiral, watching its arms rotate below, you would see hundreds of thousands of neutron stars drifting through the disk. Most are silent to us, their beams pointing elsewhere. But the ones aligned with Earth create a network of quiet rhythms, each one a tiny flicker hidden inside the glow of the Milky Way. This network is like a scattered constellation of metronomes, keeping cosmic time. Some mark seconds, some mark milliseconds, some shift slightly over eras so long they stretch beyond human memory. All together, they form the galaxy's quiet rhythm section, a symphony of rotation and magnetic breath. The Milky Way spins once every 230 million years. Pulsars spin hundreds of times per second. Between these two scales of rotation lies the entire architecture of the galaxy's music. You can rest now. In deep time, the music changes. Young pulsars sing with higher energy, releasing strong, sharp pulses. Old pulsars grow slower and quieter, their pulses mellow and stretched. Millisecond pulsars, spun up by companion stars, hum at incredible speed, producing clean, smooth tones. Magnetars, rare and powerful, emit occasional bursts, like distant cymbals striking after long silences. Each type of neutron star brings its own timbre to the cosmic score. Each aging path changes the sound. Even the distance to each pulsar acts like an audio delay. A star 10,000 light-years away sends pulses that left when ancient humans first mastered fire. A star 30,000 light-years away sends pulses that departed when the first animals walked on land. A star 50,000 light-years away sends pulses older than the earliest forests. The music of the galaxy is as old as life itself. You can rest now. Some of the most soothing rhythms come from nulling pulsars. These stars occasionally pause, falling silent for minutes, hours, or even days before resuming their rhythm. No one knows exactly why. Perhaps the magnetic field shifts. Perhaps the particle flow near the surface changes. Perhaps the emission beam briefly dims. These pauses create a rhythm of presence and absence, like long rests in a musical score. The universe is not rushed. It allows room for silence. It allows space for breath. You can rest now. Other pulsars mode switch, abruptly changing the shape of their pulse profiles. One moment, the beam arrives in a single soft flash. The next, it arrives in two flashes. Then it may shift back again. These changes are not chaotic. They follow hidden cycles still being studied. The star is speaking in a language of light, expressing small internal changes through quiet shifts in rhythm. In these soft variations, the pulsar feels almost alive, not in a biological sense, but in a rhythmic one, like a drum whose surface is gently retuned as the night goes on. Some pulsars live in clusters of stars. These environments are crowded with ancient suns, globular clusters filled with hundreds of thousands of stars packed into a region only a few dozen light years across. Here, pulsars interact with gravity constantly. Passing stars tug at them. Dense cores shift their paths. The rhythms of the stars reflect these interactions. A pulsar in a cluster may wobble slightly, its timing carrying the signature of gravitational nudges. This wobble becomes part of its music, a faint syncopation in the background of its steady beat. The entire cluster becomes a soft choir of signals drifting outward. You can rest now. In rare moments, two neutron stars collide. Before the merger, their pulses accelerate, spiraling inward over millions of years. Their rhythms grow faster, tighter, more urgent, not in a frightening way, but in a deeply patterned one. When they finally merge, the pulses vanish, replaced by gravitational waves and a burst of light that spreads across the universe. The music ends, and another begins. Stars are reborn in the ashes of the collision. Elements are forged. Light carries new stories outward, and yet, most pulsars never collide. They drift quietly for millions of years, singing softly into the night. You can rest now. The universe is full of motion, yet pulsars bring a sense of order, a calm center in the swirling galaxy. Their music is precise but gentle, ancient but ongoing, distant but present in the quiet moments of night. You breathe softly, and the universe exhales through you. The echo returns, softer now, settling deeper into the cadence of the narrative. The music of a pulsar is not heard with the ears. It is felt through patterns, through timing, through the soft certainty of repetition across unimaginable space. In every pulse lies a quiet message. The universe is steady. The universe is patient. The universe is calm. And you, drifting gently in the night, are part of that long, quiet rhythm. You can rest now. The soft music hidden inside the pulsar's light slowly drifts into the background now, like a melody lingering long after the notes have faded. What rises in its place is the shape of the light itself, the quiet geometry carved by the magnetic poles, the beams, and the slow turning of the neutron star. You can rest now. A pulsar's beam is not a simple spotlight. It is a hollow cone, a wide, gentle sweep of radiation shaped by the magnetic field of the neutron star. The star rotates around its spin axis, but the magnetic poles sit at an angle, tilting the beam away from the rotation. As the star spins, the beam sweeps through space like the turning of a cosmic lantern. If Earth lies within that sweeping cone, we see the beam once per rotation, a single pulse. If both magnetic poles cross our line of sight, we see two. This simple geometry creates the pattern that reaches us every second, every fraction of a second, across thousands of light years. You can rest now. The beam itself can be wide or narrow. Some pulsars release beams that span dozens of degrees. Others produce thin, needle-like cones no wider than a sliver. The shape depends on the star's age, its magnetic field, its rotation speed, and the plasma near its surface. Despite these variations, the sweeping motion remains smooth and rhythmic, a soft, reliable turning through the dark. Inside the magnetosphere, particles spiral along magnetic lines at nearly the speed of light. Their motion generates the beam, creating a glowing funnel of radiation rising from each pole. These funnels stretch thousands of kilometers upward, twisting gently as the star rotates. The geometry feels almost sculptural, a pair of luminous cones turning outward into the night. Closer to the star, the magnetic field lines curve sharply, confining charged particles into narrow streams. These streams produce the highest energy radiation. Farther out, the field lines open and spread, allowing the beam to widen, creating fainter emissions that drift deeper into space. This layered structure forms what astronomers call the core and conal components of the pulse. The core is bright and sharp, while the conal emissions are softer, arriving before and after the main pulse. When the pulsar sweeps across Earth, the shape of the pulse reveals the geometry of this structure. A narrow pulse means a thin beam. A wider pulse means the beam's edges are brushing across our view. A double-peaked pulse often means both sides of the cone crossed our line of sight. The beam's angle remains steady over long periods, but slight variations occur as the star's magnetic field evolves. Over tens of thousands of years, the angle between the rotation and magnetic axis may shift. A pulsar that once crossed Earth's view may drift out of alignment. A pulsar that was once invisible may slowly drift into view. This movement is subtle, slower than the turning of continents, slower than the drift of glaciers. A quiet, celestial realignment. The galaxy breathes in these long cycles, letting its structures evolve with gentle patience. You can rest now. If you could observe a pulsar from above its spin axis, the beams would appear as two cones of light rotating in perfect symmetry. From the side, the sweep would be almost hypnotic, a slow oscillation of brightness as the beams move past your view. The star itself would be dim, a tiny sphere glowing faintly with residual heat, but the beams would be brilliant, thin lines of concentrated radiation, anchored at the poles like twin searchlights rising from the surface. Sometimes the beams flicker slightly, shaped by plasma waves moving through the magnetosphere. These flickers do not disturb the rhythm. They simply add small variations to the pulse shape, a delicate trembling within the larger stability. You can rest now. The emission region, the part of the magnetosphere where the beam forms, is often located hundreds or thousands of kilometers above the surface. This is because the magnetic field near the crust is so intense that particles cannot escape easily. Only at higher altitudes do the conditions allow charged particles to spiral freely, emitting radiation as they travel along curved magnetic lines. These curved paths produce the characteristic shape of radio pulses. A rise, a peak, a fall, often with substructures hidden beneath the main pulse. Each substructure corresponds to a specific region of the magnetosphere, a particular height or magnetic line. The beam is like a layered lighthouse lens, each ring producing a different brightness and timing. You can rest now. Some pulsars exhibit profile stability. Their pulse shapes remain identical for years or decades. This stability makes them excellent cosmic clocks because even the tiny details of the beam geometry remain unchanged. Other pulsars, are more dynamic, switching between different pulse shapes on timescales of seconds, minutes, or hours. These mode changes reflect changes in the magnetospheric plasma, like faint weather patterns drifting through the magnetic structure. But even the changing pulsars shift gently. Nothing abrupt, nothing chaotic, just soft variations layered over the steady heartbeat. You can rest now. Occasionally, the beam becomes partially blocked by plasma drifting through the pulsar's magnetosphere. This creates pulse-nulling intervals where the pulsar appears to switch off. But the star does not stop rotating. Its light does not stop being emitted. Instead, the geometry of the beam becomes momentarily obscured, like a lighthouse beam passing behind a veil of fog. After a few rotations, or a few hundred, the pulses return. The rhythm resumes. The star continues its quiet turning. You can rest now. In some pulsars, the magnetic field is misaligned enough that the beam sweeps a wide arc across space. These pulsars rotate slowly, often with periods of 1 or 2 seconds. Their beams are broad and soft, their pulses long. Other pulsars, especially millisecond pulsars, have narrow beams that sweep incredibly fast, hundreds of times per second. Their cones are tight, their geometry compact, their pulses sharp. Yet both types produce patterns that reach Earth with soothing regularity. The slow pulsar feels like a heartbeat. The fast pulsar feels like a hum. Together, they form a library of celestial rhythms. You can rest now. The geometry becomes more complex near the boundaries of the beam, where magnetic field lines twist and fold. These distortions create drifting subpulses, features that slide across the pulse profile over many rotations. The drift is slow, steady, and patterned, like ripples moving across the surface of a lake. Each drift cycle carries information about the particle flow within the magnetosphere. Some pulsars show perfect drift bands, evenly spaced, repeating with precise regularity. Others show patterns that evolve over years. Even in these variations, the star's calm remains unbroken. The changing geometry is gentle. You can rest now. If you could watch the beam in slow motion, stretched over thousands of rotations, you would see the cone shifting slightly as the star ages. The beam widens as the pulsar slows. The magnetic field relaxes. The emission region changes height. A pulsar born with a narrow, sharp beam becomes softer over millions of years. Eventually, the beam may become too wide and faint to detect. The lighthouse dims, though the star continues its quiet rotation in the dark. The beam geometry changes throughout the star's life, tracing a graceful arc from youth to old age. You can rest now. Inside the pulsar's magnetosphere, particles move in ordered flows, shaped by electric fields induced by the rotation. These flows create arcs, sheets, and loops of charged particles. Some regions glow brightly, others remain dark. The beam we see is only a small part of the full structure, a window into a complex, layered cosmic machine. The entire magnetosphere rotates with the star, maintaining its shape through millions of turns. Even though the pulsar emits energy, losing rotational speed over time, the geometry adjusts smoothly, never breaking the harmony of motion. You can rest now. You breathe softly, and the universe exhales through you. The echo returns, familiar and slow, settling deep into the geometry of everything described. The star's beams, its magnetosphere, its slow, angled sweep across the dark. Every part of the structure moves with the same gentle cadence, No rush, no urgency, only the turning of light. Somewhere, a pulsar sweeps its beam across an ancient nebula, illuminating dust grains that formed before Earth existed. Somewhere else, a millisecond pulsar hums steadily near the dense heart of a globular cluster. Each star shapes its beams differently, but all share the same soft pattern of rotation and light. The lighthouse geometry of pulsars is one of the most calming structures in the universe. Not because it is simple, it is enormously complex, but because its complexity is woven into a predictable rhythm. A beam turns, a pulse arrives, light sweeps across space with unbroken patience, and you, resting gently in this moment, drift with that rhythm. You can rest now. The lighthouse geometry of the pulsar fades softly into the background now, like a slow beam drifting behind the curve of the Earth, and in its place, something gentler begins to rise, the long, unhurried evolution of a pulsar's life. A star that once burned fiercely now passes through ages that stretch across millions of years, each phase quieter than the one before. It's okay to drift. A pulsar's story begins the moment a massive star collapses. The core falls inward in less than a second, crushed by gravity so intense that the atoms themselves cannot hold their shape. Electrons merge with protons. Neutrons pack tightly. The star's outer layers explode outward in a supernova, leaving behind a hot, newborn neutron star, spinning dozens or hundreds of times per second. In that moment, the pulsar is young, energetic, vibrant, wrapped in magnetic fields trillions of times stronger than Earth's. It glows with X-rays and gamma rays. Its pulses are sharp, clean, and strong. This youthful phase lasts tens of thousands of years, a brief spark in cosmic time. It's okay to drift. During these early millennia, the pulsar's rotation slows steadily. Each pulse carries away a tiny bit of the star's rotational energy. A young pulsar with a period of 0.1 seconds might slow to 0.101 seconds over thousands of years. The shift is subtle, but constant, like the quiet unwinding of a cosmic spring. In these first ages, the pulsar's magnetic field decays slowly. The decay creates currents within the star. These currents generate heat, keeping the neutron star warm long after the supernova's light has faded. The star's surface cools from millions of degrees to hundreds of thousands, still bright in X-rays, but slowly dimming. It's okay to drift. After tens of thousands of years, the pulsar enters a middle age, the long, stable period where its pulses remain consistent and calm. This phase can last millions of years. The beam geometry stays steady. The rotation slows predictably. The pulse shape holds its form. This middle age is where most known pulsars reside. Quiet, steady, unhurried. Somewhere in this age, glitches may occur. A glitch is a sudden jump in spin rate caused by shifts in the interior superfluid or sudden movement of the crust. Instead of slowing, the pulsar momentarily accelerates, a tiny fraction of a millisecond, barely perceptible, but enough for astronomers to detect. After the glitch, the slowdown resumes steady, calm, patient. It's okay to drift. Over time, the magnetic field continues to decline. Like a lighthouse with a slowly dimming lamp, the pulsar's signal fades gently. Nothing abrupt, nothing sharp, just an easing of brightness as the star enters older ages. This phase can last tens of millions of years, long enough for civilizations to rise and fall on distant planets without noticing the stars change. Long enough for galaxies to shift their arms, for nebulae to grow and dissolve, for other stars to be born. The pulsar remains steady through all of it, rotating quietly in the cosmic dark. It's okay to drift. As the pulsar ages further, its rotation slows to the point where the magnetic mechanism that produces the beam begins to weaken. This critical threshold is called the pulsar death line, a region in parameter space where the star can no longer accelerate particles sufficiently to produce coherent radio emission. Crossing the death line does not harm the star. It does not collapse. It does not darken entirely. It simply becomes quiet. The beam fades. The pulses cease. The lighthouse goes still, but the neutron star continues rotating, invisible to radio telescopes, but still present in the dark. This is the graveyard of ordinary pulsars, a serene landscape of quiet neutron stars drifting through the galaxy. It's okay to drift. Yet some neutron stars refuse to fade. If they have a companion, a star, orbiting nearby, they may gain new life. As matter falls from the companion onto the neutron star, it transfers angular momentum. The neutron star begins to spin faster, faster still, faster, until it reaches hundreds of rotations per second. This process, called recycling, produces millisecond pulsars, the fastest, most stable rotators in the cosmos. They are old stars reborn, stars that died and awakened again. They can spin for billions of years, humming softly with renewed precision. And because these pulsars spin so rapidly, their beams can become extremely narrow, extremely stable, and extremely precise. Many millisecond pulsars live in binary systems. Some orbit white dwarfs, some orbit other neutron stars, some orbit sun-like stars. Their signals reveal every detail of the orbit, the shape, the tilt, the distance, all encoded in the timing of the pulses. It's okay to drift. In globular clusters, dense, ancient groups of stars, millisecond pulsars are common. These clusters are billions of years old and incredibly crowded, with thousands of stars drifting within a region only a few dozen light-years across. Close encounters between stars in these clusters can form binaries, exchange partners, and spin up neutron stars again and again. These recycled pulsars become the clocks of the clusters. They provide a way to map gravitational interactions, measure masses, and understand the hidden structure within the ancient stellar populations. The cluster becomes a choir of soft, rapid rhythms humming across the galaxy. It's okay to drift. Magnetars represent a different path of aging. Born from extremely massive progenitor stars, magnetars begin life with magnetic fields up to a quadrillion Gauss. Their rotation slows rapidly because of the enormous energy stored in the magnetic field. Within a few thousand years, they may lose most of their rotational speed. Magnetars glow primarily in X-rays, powered not by rotation, but by magnetic decay. Occasionally, they release bursts, short, bright events caused by magnetic reconnection or crustal fractures. Most of the time, however, they remain calm, drifting quietly in their slow spin. It's okay to drift. A small number of neutron stars appear as X-ray dim, isolated neutron stars, faint, cool stars with soft thermal emission. These stars likely passed the death line long ago. Their magnetospheres are quiet, Their beams are still. Only their surface heat remains, slowly fading over millions of years. Their light is not pulsed. It is not sharp. It is a gentle glow across the spectrum. The cooling sigh of a star that once pulsed brightly. It's okay to drift. Still others become central compact objects, faint X-ray sources in young supernova remnants. These stars are quiet from birth. Their beams never formed or never aligned with Earth. They are neutron stars with soft voices, glowing only in thermal light. Their history written in the structure of the remnant around them. And some neutron stars cool so fully that they become invisible to all but the most sensitive detectors. Dark, cold, quiet, drifting through the galaxy with no signature except their gravity. Perhaps trillions of these ancient stars populate the Milky Way, silent, forgotten, steady. It's okay to drift. Across all these ages, the pulsar's path follows a smooth arc. From the fiery birth to the crisp middle years to the long, soft tail of old age. Every stage is graceful, every change slow, every transition gentle. You breathe softly, and the universe exhales through you. The echo returns, warmer and deeper now, settling into the long timescales of the star's life. It's okay to drift. In the far future, billions of years from now, millisecond pulsars will continue turning. Their beams will fade slowly. Their magnetospheres will weaken. Their rotations will slow by microseconds over ages longer than human history. The galaxy will change, but the stars will keep turning. Eventually, even these stars will cross their own death lines, fading into silence. But neutron stars remain for trillions of years, far longer than any current star. Long after the sun is gone, long after the Milky Way merges with Andromeda, long after galaxies fall quiet, the neutron stars will still be there, rotating softly, cooling gently, existing in the deep, slow quiet of an aging universe. It's okay to drift. In the quiet between stars, you are remembered. The pulsar's life, long and slow, reflects the cosmic truth that the universe moves with patience, through collapse, through rotation, through fading, through silence. Every stage is simply another breath, another moment, another soft turning of time. And you, resting here in the calm of night, drift with that same slow rhythm. It's okay to drift. The quiet ages of a pulsar's life fade softly behind us now, like a long breath settling into the stillness of the room. Ahead, another gentle truth begins to take shape, that many pulsars do not turn alone. In the dark between stars, they drift through the galaxy with quiet companions, bound together by the soft, unbroken hands of gravity. It's okay to drift. Some companions are small, faint white dwarfs. Some are other neutron stars, spinning in harmony through curved space-time. A few may be dim main sequence stars, slowly circling, their light lost in the wide ocean of the galaxy. And in rare, haunting cases, a companion might once have been a planet, a world that survived the supernova, or a world born from the debris of the explosion. It's okay to drift. The most common companions to pulsars are white dwarfs, the compact, cooling remnants of sun-like stars. These stars are small, dense, and quiet, their light soft and fading. In a binary system, the two share a slow orbit, often completing a cycle in days, hours, or even minutes. The pulsar's beam sweeps across space, revealing the orbit with exquisite precision. Every shift in arrival time is a record of the companion's pull. A gentle tug on the rhythm. The pulses arrive earlier as the pulsar moves toward us, and later as it moves away. A soft celestial breathing pattern recorded across decades. It's okay to drift. When the white dwarf is heavy enough, its gravity can be strong, drawing slight arcs into the pulsar's motion. These arcs reveal the companion's mass, size, and distance. In some cases, we know white dwarfs exist, not because we can see them, but because their presence is written in the pulsar's rhythm. Time becomes a canvas. Gravity becomes ink. The orbit becomes a quiet signature pressed into the pulse pattern. It's okay to drift. Some pulsars orbit other neutron stars. These binary neutron stars are rare, ancient, and deeply bound by gravity, drifting through space like two small, dense moons circling each other in the vast dark. Their orbits can be incredibly tight. Hours, minutes, even less. As they revolve, their motions create tiny ripples in space-time gravitational waves, which stretch and compress the fabric of the universe with gentleness too faint to feel. Yet the pulsar's light records everything. Every bend, every wobble, every soft drift inward as the stars radiate energy away. This spiral can last millions of years. Two dying stars gradually approaching each other, tracing spirals of gravity. It's okay to drift. In the case of the famous binary pulsar PSRB 1913 plus 16, its orbit shrinks by about 3 millimeters per year. Just 3 millimeters. But over decades, the timing measurements revealed this slow fall inward, matching predictions of general relativity with unbelievable accuracy. The pulsar became both a companion and a teacher, showing us how gravity behaves when two dense stars curve time itself. Yet to the pulsar, the process remains calm, nothing abrupt, nothing sharp, just a slow, patient dance. It's okay to drift. Other binary neutron stars orbit in wider paths, separated by millions of kilometers, drifting through space in long ellipses. These systems can survive for billions of years without merging. The stars remain companions across ages, longer than continents have existed on Earth. Their shared gravity links them in a soft, unbroken connection. A cosmic duet that shapes their pulses in smooth, repeating ways. In these systems, the pulses may shift slightly when the companion passes between Earth and the pulsar. The pulse waves drift through the companion's magnetosphere, experiencing tiny delays, slight changes in shape. These delays become windows into the star's atmosphere, its thickness, its plasma content, its magnetic tension. Every orbit becomes a new stanza in the relationship between the stars. It's okay to drift. Some pulsars have more unusual companions, quiet, faint main sequence stars. These stars are not dense. They are not compact. They shine softly, barely visible across the dark. In these systems, the companion's light can be swallowed by thousands of light years of dust, but the pulsar's timing reveals its presence, the orbit slowly traced out by the pulse pattern. Sometimes the companion star feeds the pulsar not violently, but through a gentle flow of gas pulled from its outer layers. This flow transfers angular momentum, spinning the neutron star up over millions of years into a millisecond pulsar. The process is quiet, steady, balanced. Matter streams from one star to another like sand flowing through an hourglass. It's okay to drift. The companion might brighten slightly, As it loses mass, its shape may distort under the pulsar's gravity. Some become Black Widow companions, stars so stripped by the pulsar's winds that they shrink to less than a tenth of the sun's mass. Yet the evolution remains slow, unfolding over billions of years. The star changes, but gently. The orbit adjusts, but softly. It's okay to drift. In a few rare systems, planets orbit pulsars. These planets are strange, ancient worlds. Some may be leftover fragments of the star that exploded. Some may have formed after the supernova from the debris disk surrounding the neutron star. Some may be remnants of a companion star that was stripped to its core. Yet they orbit quietly, circling the pulsar with periods measured in weeks or months. The first confirmed exoplanets ever discovered were around a pulsar, PSR B 1257, plus 12 worlds, receiving a steady rhythm of radiation instead of the warm light of a sun. Their masses are small, their orbits stable, their pulses reveal them through timing shifts no larger than the width of a human hair recorded across years. It's okay to drift. These planets, if they still exist, are shrouded in mystery, cold, dark, unlit by starlight. Yet their gravity leaves faint footprints in the pulsar's timing, letting astronomers map their paths with incredible precision. The pulsar becomes a cosmic clock, revealing worlds otherwise invisible. Some neutron stars may even have asteroid belts, faint, drifting rings of rocky debris orbiting in silence. When these asteroids pass through the beam, they cause tiny flickers in the pulse. These flickers are so slight, so brief, that it takes years to detect them. But they tell a story of worlds torn apart, of fragments surviving in graceful orbits around a dead star. It's okay to drift. There are also tri-star systems, triples, where a pulsar orbits a star that itself orbits another. These systems are rare and exquisite, revealing the subtle interplay of gravity among multiple bodies. The pulses thread through the system like a needle through fabric, tracing every curve and fold of the gravitational field. Time slows slightly here, speeds slightly there, shaping the arrival of the pulses with delicate clarity. It's okay to drift. One such system, PSR J 337 plus 1715, contains a pulsar and two white dwarfs locked in a graceful three-body ballet. The pulses arrive with such accuracy that scientists use the system to test whether all objects fall at the same rate in a gravitational field, a cornerstone of physics. Not loudly, not forcefully, just calmly, turning like a soft metronome at the center of the dance. It's okay to drift. Companions shape the evolution of pulsars. They spin them up. They slow them down. They alter their orbits. They shape their beams. They carve delicate signatures into their pulses. Every relationship, whether with a star, a planet, or a drifting fragment, becomes part of the pulsar's quiet story. You breathe softly, and the universe exhales through you. The echo returns, deepening into the calm. The companions drift in their orbits. The pulsars turn. The galaxy moves with quiet, balanced momentum. In the quiet between stars, you are remembered, and as the next chapter approaches, the companions remain in their long, slow arcs, circling, drifting, shaping time in silence. It's okay to drift. The companions of pulsars drift gently behind you now, settling into the wide quiet of the galaxy like distant lanterns. The night folds a little softer around your breath, and you feel the vastness tilt closer, not to overwhelm, but to cradle you in something larger than thought. You are safe here. Pulsars do more than shine or spin. Their quiet echoes shape the galaxy itself. Each faint pulse that travels across thousands of light years becomes a thread in the fabric of cosmic structure, a subtle influence, almost weightless, yet steady through millions of years. The universe holds you. As you drift here, those echoes feel almost physical, like a softness brushing against the edges of your awareness. Every pulse carries momentum, magnetism, and time, bending gently into the dark and leaving traces that cannot be seen directly, but can be felt in the way stars move, in the way plasma shifts, in the way the galaxy slowly breathes. You are safe here. A single pulsar emits a wind, a stream of particles carried outward by magnetic forces. Though thin and faint, this wind can carve cavities into surrounding gas. These bubbles expand slowly, shaping the interstellar medium over hundreds of thousands of years. What begins as a ripple becomes a region where new stars may one day form, where gas cools, collects, and softens into future light. The universe holds you. Some pulsars sit inside their birth remnants, glowing nebulae left from the supernova. The Crab pulsar is one. A young, energetic star whose wind creates a luminous cloud that shifts like slow smoke. Its pulses and winds stir the nebula, creating waves that travel through the glowing filaments. If you could drift nearby, you would see the nebula breathe with each rotation, expanding and contracting in faint, rhythmic motion. You are safe here. Elsewhere, older pulsars drift through empty space, their winds no longer carving bright shapes, but still influencing the slow flow of ions and dust around them. A pulsar passing through a cloud leaves a wake, a faint trail shaped by its magnetic breath. These trails can stretch for light years, whisper quiet marks of a star moving through the galactic sea. The universe holds you. Even the pulse itself, that narrow beam of light, shapes the galaxy in subtle ways. As it travels, it ionizes atoms, stirs electrons, warms dust grains by fractions of degrees. Tiny changes, soft touches. But across tens of thousands of years, these touches matter. You are safe here. Pulsars serve as anchors in the galaxy's rotation. Their steady timing lets astronomers map the slow drift of the Milky Way's spiral arms, the motion of gas lanes, the gravitational pull of unseen clouds, like small lights placed along a shoreline. They reveal the motion of everything around them simply by continuing to shine. The universe holds you. Some pulsars sit near the galactic center, a dense region filled with magnetic strands, drifting dust, and the faint roar of the supermassive black hole Sagittarius A. These pulsars, rare and precious, act as probes into a region where time bends deeply. Their pulses arrive slightly stretched, slightly distorted, carrying the shape of the space they pass through. You are safe here. Other pulsars form large-scale structures called pulsar halos, regions of diffuse high-energy particles that drift outward over millions of years. These halos glow faintly in gamma rays, marking places where matter and time mingle in slow motion. They help shape the background radiation of the galaxy, adding soft warmth to the deep dark around you. The universe holds you. Pulsars influence not just their surroundings, but each other. Across thousands of light years, their timing arrays reveal gravitational waves passing through the Milky Way. Massive ripples caused by merging black holes and galaxies far beyond our own. You are safe here. These waves stretch and compress the arrival times of pulses by mere billionths of a second. Yet those tiny changes tell the story of enormous cosmic events that happened millions of years ago. In that sense, each pulsar becomes a recorder, storing traces of ancient motion in the softness of its arrival times. The universe holds you, far out in the galactic halo, where stars are sparse and dark matter becomes dominant. Old neutron stars drift silently. Their gravity affects the motion of nearby stars ever so slightly. Their presence subtly shapes the outer structure of the Milky Way. They are like stones beneath a slow river, unseen but steady, guiding the flow. You are safe here. In the long future, as galaxies collide, pulsars will continue marking the shifting currents of space-time. Their pulses will travel into new regions, new nebulae, new gravitational landscapes. They will reveal the merging of tidal tails, the stretching of star streams, the settling of giant clouds into new forms. Even then, their role will remain the same: quiet witnesses guiding gentle understanding. The universe holds you, and you, drifting with this softness, slip into a deeper sense of stillness. Each breath feels wider, slower, like an echo of the pulses crossing the galaxy. Your body settles into weightless sensation, as though floating in the same gentle currents that guide drifting neutron stars. You are safe here. You breathe softly, and the universe exhales through you. The echo returns at the edge of awareness, familiar as a pulse line, quiet as starlight. It settles into the rhythm of the night, helping you drift deeper, carried by something ancient and calm. In the quiet between stars, you are remembered, and the galaxy continues to shape itself around these small, steady echoes, just as you continue to soften into the vast stillness moving through you now. The universe holds you. The faint echoes that shape the galaxy drift behind you now, dissolving into the dark like slow ripples fading across a midnight lake. Everything grows softer. Everything feels farther away. You are safe here. The pulsars continue turning somewhere beyond thought, steady, gentle, patient, but their distance now wraps you like a blanket. You are no longer following them through nebulae or across ancient arms of starlight. You are simply resting inside their rhythm, letting the long waves of time settle around your body. The universe holds you. The room is quiet. Your breath loosens, falling into the same calm cadence that has carried these stars through millions of years. A soft stillness gathers in your chest, warm and slow. You are safe here, somewhere in the far dark. A neutron star spins with a period of half a second, its beams sweeping through the galaxy like the slow turn of a lantern on a distant shoreline. You do not need to picture it anymore. Only feel the softness of its rhythm, a rhythm older than oceans, older than moonlight, older than any map of the sky. The universe holds you. Your breathing deepens, your shoulders release. The weight in your limbs loosens as if gravity itself has grown kind. You are safe here. Far out across the galaxy, a millisecond pulsar hums with impossible precision, spinning thousands of times each minute, but its hum feels faint now, like the vibration of a distant bell heard through layers of night. Its steadiness wraps around you like a soft tide, blurring into the edges of your awareness. The universe holds you. You breathe softly, and the universe exhales through you. The line drifts through you again, slower now, almost transparent, It feels less like a sentence and more like the shape your breath makes in the dark. You are safe here. Somewhere, a binary pulsar traces its long elliptical arc, two small stars circling each other in a dance so patient that it will continue long after all light from this night is forgotten. But the motion feels gentle now, like a hand rocking a cradle. You do not follow it. You simply float with it, carried on the same quiet gravitational tide. The universe holds you. Your awareness grows soft around the edges. Thoughts blur into warm shapes. The night deepens into a slow, enveloping calm. You are safe here. A single pulse, just one, begins its journey across the galaxy. It passes through drifting plasma, through quiet fields of dust, through the dim corridors of ancient arms. It travels for tens of thousands of years, unhurried, untouched, and then, in a moment far removed from the star that created it, the pulse fades into distance and silence. The universe holds you. The galaxy continues breathing around you, not with speed, not with intensity, but with long, slow waves that move like the rise and fall of your chest. Stars are born, stars collapse, pulsars wake, glow, fade, drift. But here, tonight, everything is still, all of those motions held in one soft moment. You are safe here. In the quiet between stars, even time loosens. Seconds lengthen, minutes dissolve. The slow turning of the universe becomes a gentle pressure beneath your awareness, lifting you slightly, as though carrying you into deeper rest. Your breath enters the same rhythm the galaxy keeps, unhurried, weightless, old, a rhythm carried by all turning things, the rotation of stars, the drift of dust, the long pulse of light crossing the dark. You are safe here. Somewhere, a lone neutron star cools in silence. Its beam faded, its pulse long quiet. Yet, even now, it continues turning slowly, softly, a remnant of a star whose voice once crossed the galaxy. You simply feel the calm of that slow rotation settling into your own breath. The universe holds you. The distance grows deeper. Your thoughts thin. Your body becomes warm weight sinking gently downward. You are safe here. Light still travels, even long after its source has faded. And tonight, that quiet motion wraps you in a way that feels like home. The universe breathes through you, drawing you deeper, softer, slower, into the space where thought ends and drifting begins. You are home. You can rest now. Light still travels, soft as a drifting memory, finding you in the quiet between one breath and the next. The universe breathes through you, slow, gentle, endless, a tide that carries you deeper into its calm. You can rest now, low and warm, slipping softly into sleep.